All right, this lecture is on carboxylic acids and carboxylic acid derivatives. This is an interesting chapter, especially those of you in nutrition. You hear things like fatty acids. This is going to be the building block to those fatty acids. All right. First of all, you want to be able to identify the functional group. And again, if you're having problems with functional groups, go back to chapter 10 and look at that table of different functional groups, because that's pretty much what we're doing this semester. Is you're going to be looking at alkyl groups or aryl groups, aliphatic, aromatic, and then you're going to be looking at attachments to those functional groups attached to either an alkyl or aromatic group, or aliphatic or aromatic group. So what makes a carboxylic acid? Let's see if we get a good acid. Well, what you see right here in pink, that's what we're looking for. All right. So both of these are carboxylic acids. Again, this is going to be a precursor to fatty acids. And then depending on what's attached, if it's an aromatic hydrocarbon, and again, what's an aromatic hydrocarbon? The classic example here would be benzene. So we have a ring. And again, I saw this, when you do a benzene ring, you're either going to put a circle in it to make it aromatic, or you're going to put some double bonds in it, alternating like so, to show that it's aromatic. All right. Now we're going to go through a series of chemical reactions where this hydrogen off of the hydroxyl group is going to be replaced by an alkyl group or an aromatic group, and that's going to make an ester. All right. All right, carboxylic acid groups consist of two very popular functional groups. That's what it says, a carbonyl group and a hydroxyl group. So what are those? Well, we've been talking about carbonyl. This should be pretty much burned into your brain now. That's the carbon double bonded to the oxygen. That's where a lot of the magic happens. And then we've also looked at this group already. This is the hydroxyl group. We saw that with alcohols. And we saw the formation of aldehydes and ketones with the oxidation of the hydroxyl group. All right. What's different about this one is that we've knocked off so this part right here, you can see there's the carbon double bonded to the oxygen, and then we would have oxygen bonded out here to a hydrogen. And now we've replaced that hydrogen, in this case, with alkyl group. And this relationship between this carbon, this oxygen, and this carbon, that's going to give us an ester. And you say, why are esters so important? Many of your flavorings, like banana and so forth, are ester-based compounds. Physical properties, that's what we've said about each chapter, is you need to be able to identify not only the chemical properties but the physical properties of these compounds. So first of all, we know acids from chemistry 140 that they have a sour taste. All right, so you should remember that from the last time. This may be new. Unpleasant odors, well, they're generally acrid. They've got a burning sensation in the nose. They're generally a sour kind of smell, and that's why we generally associate these with unpleasant aromas. High molecular weight carboxylic acids, we call those fatty acids. So we've been talking about that. This is going to be really important when we go into the biological part of the book, which is coming up in a week week or two. Low molecular weight carboxylic acids are water soluble. Why? Right here's the example. So here you've got a carboxylic acid, and you go, how do you know that? Well, there's the carbon double bonded to the oxygen, and there's the OH group. So there's our carboxyl group. And remember what we said hydrogen bonding is? This is, again, something we talked about in 140, but we've seen this already in Chemistry 150, is that when hydrogen is bonded to either oxygen, nitrogen, or fluorine, hydrogen bonding can occur. So here we have a hydrogen that is bonded to an oxygen. And the same thing on the carboxyl group here. Here's another oxygen bonded to the hydrogen. So here's one carboxylic acid, and there's the carboxyl group. And here's another carboxylic acid. And so there is an attraction which is shown by these dots, which is called hydrogen bonding. Now what that is it's not a true bond. It is it's an attraction that is similar to a dipole, because that's what we have here. We've got a negative, partially negative charge on the oxygen, partially positive charge on the hydrogen. So it's a dipole, but we generally think of it as a stronger dipole than just a regular dipole. Hydrogen bonding is a more specific, a stronger form of a dipole, and therefore, what does that mean? Well, it means it's harder to separate these two molecules from each other. These are intermolecular forces, and so it's hard to separate these. That means that these are going to have higher boiling points than if we did not have the hydrogen bonding. Over here we can see again a carboxyl group, and this time it's just dissolved in water. So if the carboxylic acid is small, if this R is small on the carboxylic acid, then that carboxylic acid will dissolve in water. And again, the reason why is water is a polar substance. It has a positive and negative region, and the quick way to do that is here's what I teach in 140. If you draw an imaginary line through the molecule like this, and it's strictly positive on one end and strictly negative on the other, then you've got a polar molecule. And then if you look at this, we can draw a line through this part of the carboxylic acid, and it's strictly positive on this end, and it's strictly partially negative on this end. So again, it's a special form of dipole-dipole interaction, which we call hydrogen bonding, which again makes it hard to separate the carboxylic acid from the water, and therefore this carboxylic acid would definitely be water soluble unless R gets too long. When R gets too long, then we get into these fatty acids, because then the nonpolar part of the molecule takes over, and we know that nonpolar substances do not dissolve in water. All right, so that's what they mean by low molecular weight carboxylic acids are water soluble due to hydrogen bonding. All right, so physical properties. Here's where we're going to see it. Here we have a nonpolar butane. It has a boiling point of -5 degrees Celsius. So room temperature, it's definitely a gas, and you know that. If you've ever seen a butane lighter, you know it's a gas. And it has a molar mass of 58. All right. So here's something with a similar molar mass, but its boiling point is 7 degrees Celsius. All right, so it's above freezing. So why is that? Well, we have an oxygen here, and that oxygen creates an interaction with maybe a carbon. Another methoxyethane is above here, and we get some attraction between the hydrogen and the, or we get, yeah, like if I want to draw that out, we may get some attraction between the carbon and the hydrogen. Now, that is not hydrogen bonding. Remember, hydrogen bonding only occurs with oxygen, nitrogen, and fluorine. So over here, we do see the oxygen is directly bonded to the hydrogen. So we get that oxygen and then out of shape here is a hydrogen. This is partially negative and this is partially positive. Now we get the hydrogen bonding, and watch the boiling point dramatically increases. More mass is the same as methoxyethane, but this one propanol has a much higher boiling point because we now have hydrogen bonding present. All right. This particular, this second line here, I was just trying to show you that, again, there's going to be attraction here between this oxygen and maybe another hydrogen. It's not hydrogen bonding because this oxygen does not have a hydrogen directly attached to it. And then again, we see a little bit of a change here with the ketone. All right, so this aldehyde, this is ketone. But wow, when we get that OH again, where we get the oxygen bonded to the hydrogen, and we get that structure just like we saw up here, notice the boiling point increases dramatically. So what you want to get out of this slide is hydrogen bonding is key to increasing boiling points. All right, nomenclature, naming. Determine the parent compound. 4 carbons long, it's butane. Number the chain so that the carboxyl carbon is carbon number 1. All right, so this is something you're going to have to keep in mind. I think that's what I see, like I saw in the last the last quiz, last exam. Some of you misnumbered, like that when we have a double bond, when we're talking about an alkene, that takes precedence over like a functional group. So here, though, with a carboxyl carbon, that's going to be carbon 1. Replace the ending with oic acid. This is IUPAC. So this becomes butanoic acid. All right. Now, I will say, and that's going to be difficult about this chapter, because we're getting into fatty acids and we're getting into substances that have been studied extensively, both in chemistry and biology, there are going to be common names for these compounds. I mean, I'd love to stick with the IUPAC name, and maybe one of these days we will, but I can tell you the common names for these compounds are still used a lot. All right, so like this one. Whoever has heard this called ethanoic acid? I mean, that is the name according to IUPAC. It's easy. It's 2 carbons, and we know that's from ethyl or ethane. And so, and this is a carboxylic acid because we see the functional group right here. So yes, the easiest thing to call this would be ethanoic acid. But I can tell you about 99% of the time we still call it acetic acid. Acetic acid is the substance in vinegars. It's again, vinegar, like apple cider vinegar, about a 5% acetic acid solution. All right, so here is where we're going to learn some of the naming. Again, the carbon that contains the double bonded oxygen and hydroxyl group, that is always going to be carbon number 1 when we're naming carboxylic acids. So this is carbon number 2, and this is carbon number 3. So this hydroxyl group is on carbon number 2. So the longest chain is 3 carbons long. So that's where we get the propane. And propane, because it's a carboxylic acid, gets the oic acid. And then to tell the person there's this hydroxyl group, we say 2-hydroxy propanoic acid. Now, that is the IUPAC name. But I'm going to tell you, again, this is a pretty common substance in biology, and they call this alpha hydroxy propionic acid. And so what's going on here is this is the first carbon. The next to carbon to it gets the alpha designation. All right. So here, again, we identify the carboxylic acid carbon. That's carbon number 1. We know this is 1, 2, 3, 4 carbons long, so that's where we get the butane, which would be butanoic acid. So we would say 3-methyl butanoic acid. But again, the common name, this is alpha, this is beta, oops, this is beta, and so this would be beta methyl butyric acid. So in the common name, these carboxylic acids get names like that, butyric acid. All right. Again, here, so here's what, I mean, this is where IUPAC is going to be better than. How many people know that as adipic acid? I mean, you may have heard of it. I've actually worked with adipic acid before. I was one of my experiments when I was in graduate school was to see how much adipic acid was coming out of this chemical plant and how much it was contaminating the water stream. So, I mean, it gets to be where you have to memorize all these different names, and that gets to be different. Although I've heard, maybe you've heard of malonic acid. That's a pretty common one. But so what's going on with this one? Well, look at your longest chain. 1, 2, 3, 4, 5, 6 carbons long. And notice you've got carboxyl groups on both ends of the molecule. So I saw this on the exam too. When you have 2 of a functional group, you've got to indicate that with the di here, whether it's a diene, in this case it's dioic acid. It's a dicarboxyl group, so dioic acid, and it's 6 carbons long, so hexane dioic acid. See, you can figure that out. That's what I like about IUPAC. You can figure it out, and if you don't know the common name, I mean, it's where you get stuck. I mean, so I really like IUPAC, but I know the common name still, like I said, very important. So again, I don't want to go through all these, but again, here when you see 2 carboxyl groups, don't forget the di. That's the only time you use dry. If you have 2 of the functional group, diene, diol, we had alcohols, there were 2 OH groups. Like if we knock this off and knock this off, we'd have a hexane diol. That's another thing. The name doesn't change that much. Like the hexane still stays the same, and then that diol tells you it's a functional group, and in the case with the carboxyl groups, it's dioic acid, so it helps you name these much easier. All right, so here's where they talk about the carbon next to the carboxyl group, alpha, beta, then we go gamma, then we go delta. All right. Again, these are common names. Common names. All right, so what would I like to say about this page? You may want to make flashcards of these. That's what I would say. Make flashcards. And on the flashcard, I would put formic acid on one side, methanoic acid maybe on that same side, and then have a structure on the other side. So make a flashcard with this part on one side, this part on the other side to help you know these. I mean, these are important. Formic acid, maybe you've talked about fire ants and that they release formic acid. Generally is what caused the blister when a fire ant bites you. Acetic acid, again, common acid. This is what we saw ethanol being converted to in the liver. So when you oxidize ethanol. Butyric acid, you hear this stuff when we're talking about butter, rancid butter. That's what I always remember about butyric acid. And once you smell rancid butter, it really starts to turn you off from it. And then these right here are goat fats. In fact, that's what this part comes from right here, Capricorn. So that's it is something to remember, or palm oil, palmitic acid. So, and stearic acid, this is a really important one too. Beef fat, tallow. All right. So here they show you where the root for those common names come from. But see, you have to know all of these, and I think that makes it kind of difficult. But I can tell you, my professors, I mean, they knew them as the common names much more readily than the IUPAC names. So, like I said, I think it's really important. These are the really important ones. These are the ones that's going to come up over and over again. So I would make flashcards for those. All right. Now we're switching. Everything we've been talking about up to this point was aliphatic carboxylic acids. Now we're getting into the aromatic carboxylic acids. What makes them aromatic? Because you've got an aromatic ring attached to the carboxyl functional group. All right, so this is a real common one, benzoic acid. We know that if you didn't look at this carboxyl group here, you would say this is toluene. So this is toluic acid. And see, when you get that IC there, that's telling you. And then what's the M stand for? Meta. Remember, there's ortho and there's meta. All right, so keep that in mind. Oh, in fact, they show it right here. Here's a orthobromobenzoic acid. So it's a carboxylic acid. So there's the benzoic acid. This is carbon number 1 here. So we know if it's ortho, the bromine's off of the carbon number 2 there. All right, metabenzoic acid, and then the dicarboxylic acid, which again, common name, phthalic acid, and most people call it that. All right. All right. So this one gets a little. There's different ways to think of this part. One is, if you focus on this, and this is 2 carbons long, all right, we would look at that and say, oh, that's aliphatic, that part is, and that this would be ethanoic acid, all right? So it's a carboxylic acid, and we would call it ethanoic acid. So now you're going to think of this part as attached to that chain, and so that's where we get the 2-phenyl ethanoic acid, because this is the first carbon and this is the second carbon. All right, 2-phenyl ethanoic acid. Or you can use the alpha symbol if you're using the common name. Remember, that's the common name down here, alpha phenyl acetic acid. But if you're going to call it by the common name, then you're not going to call it ethanoic acid. You're going to go by the common name for this aliphatic carboxylic acid, acetic acid. Same thing here, propionic acid. It's 3 carbons long. That's how we know it's propane. And to me, the IUPAC is the best way to go here. But like I said, when we get into the biological part, you're going to hear the common names a lot more frequently. So think of this as a functional group, the phenyl group. I think that's the best way to think of it. It's just a functional group attached to the carbon chain. All right. For this page, I think you probably ought to memorize most of these. Again, these are so common. They come up so much. Like I said, I'd probably put on one side of the flashcard the IUPAC name and the common name. I mean, I still use this one. Maybe you remember this one, oxalic acid. Again, it's an acid because, again, it's a carboxyl group. There's one here, and there's one here. And it's these hydrogens that are acidic. They can break off and give us an acidic solution. Notice this is a dioic acid. If you're looking at it in terms of of the IUPAC name. Again, that's why I like it. You look at oxalic acid and you go, you don't know that that's a you don't know that that's a dioic acid. You don't know that it's two carbonyl or carboxyl groups. So that's the advantage of IUPAC over common name. All right. Propane dioic, butane dioic, pentane dioic, and hexane dioic. Again, you're going to see these come up frequently. I will say this: one thing I saw on that on the exam is, and maybe I need to make a video of it. Just let me know. But a lot of you missed the condensed formula. I like structural best, or I like line formula. Actually, these are line because they're not showing all the hydrogens. Line formula, I think, is probably one of the best. It's easiest to draw, and we're probably going to see more line formulas. It's something a little newer to me. It's not something it's not my most comfortable structure. My most comfortable structure is just do a structural formula. But after structural, the next thing we were generally taught was condensed formula, and line formula a little newer. So condensed formula takes a little bit of practice, and I did see people miss the condensed formulas on the exam. So you may want to go back and practice the condensed, because we're going to be doing probably more condensed as we move through these chapters, because we're going to get into larger and larger molecules, especially when we start talking about biological systems, and you can't write it all down. So it's either going to be condensed or it's going to be lined. You're not going to be doing large structural formulas. All right, so where do we see carboxylic acids? Complex carboxylic acids in a variety of foods, generally in the form of fatty acids. Citric acid found in citrus fruits. Lactic acid, you've heard of that. Tartaric acid, that's in baking powder. The tartaric acid it makes the it gives you a finish on the dough, like it gives you kind of that crust on the dough when you bake bread. We're going to see that. And then malic acid gives us the sour tasting green apples. All right. Notice the citric acid, you start looking at that and you start, is that a sugar? Well, no, because it's got these carboxylic functional groups on it. Kind of reminds you of a sugar there, doesn't it? Do you think you can convert a sugar to an acid? All right. Lactic acid. This is one you guys exercise a lot. Lactic acid buildup. Tartaric acid, really interesting if you read some of the history of tartaric acid. And then malic acid. All right. Oops. I'm really going crazy here. I just found out the wheel on my mouse spins through these slides. All right, that's where we're going to stop at, because what we've done so far is we've just looked at structure, we've looked at physical properties, we've looked at common names, we've looked at IUPAC names, and some manipulations of that. And now we're getting into the reactions. In fact, this is oxidation. So we'll stop here, and then the next lecture will be on the oxidation of, or the reactions of carboxylic acids. All right. If you need other videos, just email me. I'll be glad to make them. I hope these videos are helpful. I didn't get a lot of feedback after Chapter 12. No one requested a video for Chapter 13, and I saw some errors on the exam because I felt like because of that I didn't talk about acetals or hemiacetals. So I felt like, well, maybe we should have done a video. So this is the way I communicate. I have to get feedback from you, though, to tell me, is it worth it, or is there something I need to slow down on, or is there something you need more examples of? So please communicate with me. We have to do this through email. It's just like I'm in the classroom, and the way you're communicating with me is through email, whereas in the classroom you just raise your hand or speak up. All right. Thanks a lot, and we'll see you later.